Hi, welcome back. I'm Professor Ronald Vincent M. Santiago, and today we'll be discussing Module 24, which is Case 3, Faults on Power Systems, Loaded Condition. Now, as an additional modeling techniques, for the utility side, let us recall that the MVA under short circuit is equal to the MVA base multiplied by 1 over the Thevenin reactance at the fault point. Here, the MVA at short circuit is for three-phase fault, and the reactance, Thevenin reactance under the fault is the positive or negative sequence reactance. To compute for the MVA under short circuit for the specified fault, that will be equal to the square root of 3 multiplied by the voltage multiplied with the short circuit current. Note that the utility is always connected three-phase, 4-wire, Y-grounded, and the positive and the negative reactances are equal. Let's consider an example 1. The fault MVA at the 138 kV utility bus is 875.3 for a three-phase fault and 617.2 MVA for a single line to ground fault. Let us assume that the positive and the negative reactances for the utility bus and connected Y-grounded are equal, and let us determine now the per unit reactances X1, X2, and X0. We're going to use a 100 MVA and 100 kV as the bases. Now, to compute, for the utility, we have the short circuit MVA for a three-phase fault to be 875.3. The MVA for short circuit under the single line to ground fault is 617.2. X1 now, the positive sequence reactance, is equal to kV square divided by the short circuit MVA, which is now equal to 21.76 ohms. Here, we can say that X1 is equal to X2. The positive and negative reactances are equal. Now, to compute for the zero sequence reactance, let us consider now the fault current for a single line to ground fault. That is equal to 3 times the phase voltage divided by the sum of the positive, the negative, and zero sequence reactances. So, to compute now, that is equal to the MVA under short circuit for a single line to ground fault divided by the square root of 3 divided by the line voltage, which is now equal to 617.2 MVA divided by the square root of 3 divided by 138 kV. So that gives us a magnitude of a fault current for a single line to ground fault, 2582.253. Now, solving for X sub 0, so using our formula, so we now know the MVA at short circuit for a single line to ground fault, which is 2582, is equal to 3 times the utility voltage of divided by square root of 3 divided by 2 multiplied by 21.76 plus the value of the zero sequence reactance. So solving for X sub 0, so that gives us 49.05 ohms. Our X1 and X2 are equal, which is equal to 21.76 ohms. For the 3-winding auto transformer, so given this diagram, we have a single winding, and a tap is brought out for the secondary winding having the winding NX, and another winding on the secondary side represented by the winding NY. So having these parameters as is illustrated in the diagram, we can have some ratios. VH over Vx is equal to NH over NX. That is the proportionality of the voltage to the number of turns. And similarly, VH over Vy equal to NH over Vy NY. And Vx over Vy is equal to Nx over Ny. So with this, we can generate the magnetomotive force Nh times IH, which is equal to Nx Ix plus Ny Iy. And this is the equivalent circuit of an autotransformer. So you have the parameters, the relationship JHX is equal to JH plus JX, JHY which is equal to JH plus JY, and JXY is equal to JX plus JY. And from here, we can generate formulas solving for JH, JX, and JY. JH is equal to 1/2 multiplied by the quantity JHX plus JHY minus JXY. For JX, that is 1/2 multiplied by the quantity JHX minus JHY plus JXY. And for JY, that is equal to 1/2 times the quantity negative JHX plus JHY plus JXY. As an example, let us consider 3-winding 3-phase transformer which has the following nameplate rating. For the high tension side, H, we have 30 MVA, 140 kV. For the low tension side, X, that is 30 MVA, 48 kV, Y connected. And the capacity is 10.5 MVA, 4.8 kV. Now, the short circuit test will yield the following impedances. JHY, which is 63.37 ohms at the H side. JHY is 106.21 ohms at the high tension side H, and JXY is 4.41 ohms at the X side, at the low tension side. Now, we're going to find the equivalent circuit in ohms, referred to the high tension side H. So, JXY, we can now compute for this, that is equal to 140 over 48 square multiplied by 4.41, which gives us 37.52 ohms. So with all the impedances referred to the high tension side, we can get now JH to be equal to 1/2 multiplied by the quantity 63.37 plus 106.21 minus 37.52, which gives us 66.603 ohms. JX is equal to 1/2 times the quantity 63.37 minus 106.21 plus 37.52, and that gives us negative 2.66 ohms. And JY, that gives us 1/2 multiplied by negative 63.37 plus 106.21 plus 37.52, and that equals 240.18 ohms. So with these values of JH, JX, and JY, we can plot that in the equivalent circuit of the auto transformer. So that ends our module 24. See you in the next module.